So good morning. Hope you done the CRE exam well. Please see for the answers in Gahani, and if any difficulties are there, we will discuss. Any difficulty in the question paper, no? Any difficulty in the question paper? You can check for the answers. Everything is given in the Gahani. So please try to do what problems at least I gave. Straightforward problems I gave. Good problems. Please read once and twice the question paper, and then having that answers with you. 1 second. There's 2 minutes. Your cleaning is going on. I'll just come. Okay, sorry for the disturbance. There was some cleaning going on. Okay. How many people are there? Just want to see now. Only 617. What happened? Why people are not joining? Rohit, what happened? Rohit?
Sir, yes, sir.
Yeah.
I don't know. Maybe it's the first period. I think
They are
time.
taking their own time. Okay, okay. That's only that, or I thought something else parallelly is going on, so people didn't join.
So tomorrow
Not
we also have an elective exam.
exam,
Yes,
no?
sir.
Exam tensions. Okay, okay. Don't worry much about the exam, right? It will
Yes, sir.
not
Yes.
be, about other exams. I don't know. Don't much bother about CRE exam. I'll take care of it. Okay. So just listen to the theory part, how it is being done. Again, as I earlier itself told, don't read for getting the marks, right? Instead of that, try to understand the subject. Marks
Sir,
automatically. Yeah, go
you
ahead.
haven't told the answer for the two questions. Why PFR takes less volume than CSTR and why
Already
the batch equation
we
same?
told, right? Because the concentration is dropping. So in CSTR, the concentration is dropping suddenly. So your rate will be directly proportional to the concentration. So concentration less, rate will be less. So rate is less, your conversion will be less. Or if you want for the same conversion, your volume should be bit more. This already we discussed. No? Yeah.
So YP
Any
is PFR batch equation and performance equation
that
same.
you have to tell you. So at least some of you should tell the answer. Then only we will discuss and then give. Right. On my own, if I give, then you won't have the discussion. At least since I didn't give the answer, it is still ringing in your mind why it has happened. Right. Correct. I appreciate your effort. At least you remembered still the questions what I put. Good. Good. Yeah, it starts ringing in your always. Why? Right. That's good. That's good to know. I want that to happen for everyone. Right. So think about, and if some people are giving some good answers, then we will discuss. Right. This answer, I think it was given in the previous discussions. That is why I opened that thing. Right. Like that, there are a lot of what you call open-ended questions in CRE. I asked some questions. I think I don't know how many of you still remembered why that recycle reactor turns to MFR. How it will. What is that derivation? That no way concerned with the thinking. It is just thinking about only how to solve that right the integration, right? Okay, good. So I think now some people are joined 25. Let us start today's discussion. So in the last class we were discussing about this selectivity and all, right? In a parallel reactions, this one important thing is the selectivity, that is the moles of the desired product to that of the moles of undesired product. So is it the only way to know whether or to have our desired product? Is it the only way? Only about selectivity you want? How you can do the selectivity only by whatever discussions I gave here? Is it the only way that is having concentrations higher, or if the order is high, keep the concentration high so that R is formed? That is what I'm just discussing. Either it is in a parallel reaction or a series reaction. So depending on whatever reactor it is, so whatever concentration you want to keep, accordingly you keep either in CSTR or PFR. That is what I'm just giving. Is it the only way? That is one more open-ended question. Is it the only way to get the desired product? There is another way also. The another way is what you study in CRE2, that is catalytic. You can find a catalyst. Catalyst, what is the main purpose of the catalyst? The main purpose of the catalyst is to increase the selectivity. That is the important aspect of the what do you call catalyst. Generally, we tell that catalyst enhances the rate and everything. That is true. But the one more main purpose of the catalyst is to enhance or the selectivity. Selectivity in the sense, what is the desired product? So it should give you more desired product than and suppress the undesired product. So if you can find a catalyst where you get more of a desired product, that is absolutely fine, right? So that we'll do in the next semester. That is how we choose the catalyst and all, right? So since the catalyst is not involved, we are just playing with the control of the concentration or the having the choice of reactors, what combination is better, all that we are discussing. That is only qualitative analysis, right? So this is what is the parallel discussion, that qualitative and both quantitative. Quantitative, it will come in terms of instantaneous yield and overall yield. For instantaneous yield is moles are formed by moles A reacted. You have to calculate this. Using this, then you have to calculate the overall fractional yield. So if it is a PFR, you have to put that what instantaneous yield here and then calculate this. Or if it is in MFR, then you already calculated the instantaneous yield. From this expression, we can calculate what is the overall yield in MFR. In PFR or MFR, you can calculate your, if it is a staged process, this particular formula, and whatever PFR or MFR, if you want to find out the final concentration of the product, then this is the expression. Whatever it is, the phi if it is for plug flow reactor, you have to put pi p, or if it is a mixer reactor, you have to put pi m, whatever you calculated. That is nothing but that into the concentration difference will give you how much of the R is formed, right? So this, based on this, we did some problems also. The problems are very important. Definite question, it will come in the exam. No, not only in your cycle test, even in the final exam, it will come, right? So I done some 3 to 4 problems. Still a lot of problems are there. I'm not having much time to look more problems, because you know its syllabus is vast. We have to complete. So that's why we are going for the next discussion, that is the multiple reactions, especially series, right? So we'll see the series reactions. Already we discussed this derivation. A is giving R and giving S. So sometimes R will be your desired product, or sometimes S will be your desired product. So anything it can happen. So A is giving R and giving S. So if you write in terms of the rates, minus RA is minus dCA by dt, K1CA, and RR, that is the overall net rate of formation of R, is dCr by dt is K1CA minus K2CR, and the formation of S is dCs by dt is K2CR. So from this we can calculate how much is Ca by Ca naught, Cr by Ca naught, Cs by Ca naught from these expressions. So to do that, what you have to do, this dCr by dt, you have to take this K2Cr this side, and this will be in a form of a differential expression. The solution already we discussed in the previous classes. Am I audible, ma? Some sound came in between. Hello?
Yes, sir.
Okay. Some sound suddenly came. Yeah. So we'll discuss about the qualitative discussion first. We earlier itself, last class we discussed this, and if you want this combination, that is A is put, and then entire A is being, you are assuming that the reaction is happening in presence of the light. So entire A is being, what do you call, lighted, or reacted in presence of the light, to give you the A concentration will come down, the R concentration will go up till certain extent, and then as the S is being formed, the R concentration will come down, and the S concentration will go up. So you will have a maximum somewhere. So if you are discussing about R is going to be my desired product, then it is always better to go for this kind of arrangement. So entire A you get reacted first, and then to give you maximum R, and try to maintain the concentration of R maximum, so that you will get it, right? So other than that, if you are going to be, S is going to be your desired, then you don't want the R formation. What you do is, you can do like this: instead of entire A is getting reacted, you take sum of A, that is pumping sum of A, and then reacting in presence of the light. So here I am giving just one example here, that the reaction is happening in presence of light, just to make the points clear. That does not mean that this reaction is happening only in the presence of light, right? Just to make the discussion clear only, he gave here. Then that react product is again recycled. So in this product, what will happen is, see here the intensity of the light is same. The intensity of the light is being falling on the entire A, but here the intensity of the light is same. The intensity of the light is falling only on certain amount of A. Therefore, A gets completely converted because it is having more of the light source. So practically what you get, you won't get R at all. You get A is completely converted to R. Yes. So no R is formed. That is what it is being shown here. So it depends on what product you are interested. If you are interested for an intermediate, then this is how it should be done. And if you are interested in the final product, not the intermediate, then it is better to go for this kind of arrangement. So from the qualitative analysis, we discuss these are the things which is important. The mixing is plays a very important role. So for irreversible reactions, only for irreversible. If it is a reversible, then the condition will change. So we are seeing only for a irreversible reactions here. That is, A is giving R. It's not that R is again giving A. If that is the case, then these conditions are not good, right? For irreversible reactions in series, the mixing of the fluids of different compositions is the key to the formation of the intermediate. So here the mixing plays a very important role. So the maximum possible amount of any and all intermediate is obtained if the fluids of different compositions and at different stages of conversions are not allowed to mix. What does this statement gives? The maximum possible amount of any and all intermediates is obtained if the fluids of different compositions and at different stages of the conversion are not allowed to mix. Here what is happening? The fluids of different ages and the fluids of different conversions are allowed to mix here. That is why you are getting some of A or more of A. But if this is not being done, here what is happening here? Entire A is getting converted and only the product is formed. The product is nothing but S. So only one conversion is being there. So you are not allowed to mix of the different ages of that and different conversions. Here the conversion is 100%. So IS is 100%. That is A here is 100%. There is no practically A here. So whatever A is present, only here it is being there. That is why that is the condition. The maximum possible amount of any and all the intermediate is obtained if the fluids of different compositions, there is no fluid of different compositions here. And at different stages of conversion, there is no different stages of conversion here. Only one conversion are not allowed to mix, right? So that is the big statement here. So based on the above statement, the effectiveness of various reactor systems are, we already know that PFR and batch will give you maximum of R and CSTR or MFR should give maximum of, should not give maximum of R. That we already discussed in the previous class. So based on this particular thing, you know that PFR and batch will give maximum of R, CSTR will give a minimum of R. So based on this discussion, I'll show you some arrangements. You tell me whether left side is good or right side is good, right? So this is the reaction. A is giving R is giving S, and we want the formation of R to be more. That is right. So for that condition, PFR and batch reactor will give maximum R, and CSTR will not give maximum of R. So you tell me here in this particular thing, which is good and which is bad. There is one side 4 combinations A, B, C, D, and here also for A, B, C, D. So A is this combination, B is this combination, C is this combination, D is this combination. Now tell me, in A, left side to your left side is plug flow, and right side is mixed. So which is better? Favorable contacting patterns for any set of irreversible reactions which is in series, right? So series or whatever, which is better, left side or right side? So left side is plug flow and right side is a mixed reactor. So favorable contacting pattern to give you maximum R will be plug flow, because here different ages are not allowed to mix. That is what he is giving you. The maximum possible amount or intermediate will come when you are not allowed to mix of different stages of compositions and conversions. So here there is no mixing. Therefore, this is favorable compared to this, right? Now, what is happening in the B? Yeah, here R is 1. So recycle ratio is 1. That means 99 parts is going here. Here it is 100 parts in the sense 99 parts is going here. 1 part is coming back. So this again is a plug flow. Yeah. Which is better, left side or right side?
Right side, sir.
Right side. Any other answer other than that? Before that, yeah, think about why right side is better. Yeah, any other answer? Anyone is telling about left side? Yeah, I stick with the left side. Any answer for that? Is it correct? What I'm telling? Favorable condition is left side, I'm telling. Anyone agree with me or disagree with me? Emma? No one is talking. No one wants to open their mouth. Yeah, again, I repeat to you, if you're not opening your mouth, you will be there only. Understand? So, in Telugu, there will be one proverb. I don't know how many of you understand that. ఎక్కడ వేసిన గొంగలి అక్కడే. That means you will be where you are if you are not questioning or something like that. Right? So, if you want to question, if you want to go high or learn the subject or something like that, you should always put questions to yourself. Right? So the right side is better, is not the left side, as earlier you pointed out. What I told is wrong. This is mixing is happening here, even though it is plug flow. There is a little bit of mixing. So if there is a mixing happening, you won't get R formation. That is what here he's giving you, right? So here there is a mixing, but there is reactors in series. So what will happen is here you get it will be just like a plug flow reactor because more CSTRs in series, it will be like a plug flow reactor. Yeah, what about C combination? So here one reactant is being circulated here and one more here, right? So one reactant is
Eight sides.
continuously going. And this side it is just like this combination. So which is better here? Yeah, again right side because we know it is plug flow. This is going to be a plug flow, right? This is all mixing and all, right? So last one, laminar and turbulent, which is better? Laminar is better or turbulent is better? So both are what do you call PFS? Which is better, laminar or turbulent?
Laminar, sir.
Laminar, you know what is happening? The velocity of with which it is going is very low. So turbulent in the sense the velocity of the liquid which is going inside is more. So where the mixing will happen? In turbulent or laminar? Huh? Turbulent it will happen or laminar? Ideally, think about ideal. Right. So the velocity is going out much higher here. Therefore, there may not be a great mixing here in ideally, but non-ideally you get a different of mixing. Laminar in the sense you know that there will be sticking here. So the particles which are sticked at the inner walls, it may not move with the same velocity as that of the center. Therefore, here at different compositions are you are making it to mix here. That is why this again it is better. Right? So turbulent, ideally turbulent is better because you get any property in this particular radial direction. Everything should have the same velocity. That is what is the ideal turbulent means, right? So that's less mixing, all that, right? So we'll go for a quantitative treatment. So let us go for a quantitative treatment. When we are discussing about this quantitative treatment, we should discuss for a batch reactor and MFR. So let us discuss for a PFR or a batch reactor. This already we discussed in the previous class. For a batch reactor, we discussed the same equation can be written for a PFR because the design expression of batch and PFR is going to be same. So just we'll repeat again. A is giving R, giving S. So RA, RR, and RS you are writing. So we assume that initially no R and no S is there. Only A is present. Therefore, let the concentration of A is Ca naught. So this is the expression dCA by dt is K1Ca. You are writing Ca as Ca naught into 1 minus Xa. And then rearranging, you can get Ca by Ca. Ca is Ca naught into e power minus K1t. Take the integrals. Take the integral for this and then take Ca this side, dt this side. dCA by Ca is ln. Substitute the limits. Then you get this. So like that, we can get the concentration of R. So concentration of R is, this is the expression dCr by dt. This Cr also you take this side. So this dCr by dt plus K2 Cr is K1 Ca naught e power minus K1t. The solution for this is in the form of like this: dy by dx plus py is equal to q. So whatever is the differential here, here it is the same thing, CR and CR. That is what here. Y is differentiated with respect to X and Y is present here. So for this kind of things, there is a what do you call solution for it. Y into e power pdx is equal to integral q into e power integral pdx dx plus c. So based on that, what is y and what is p, what is q and what is p, all that it is given here. So if you substitute in this particular thing, you get this expression. Then try to do the integrals and take whatever like terms to one side. Here initial condition is CR naught is 0 at time t is 0, because at time t is 0 there is no R which is being formed, only S is being there. If you substitute this limit, then the integration constant you get. Substitute this integration constant here and then calculate CR by CA naught. So CR by CA naught is this expression. This already we derived in the previous classes. I'm not giving much importance to it. Now we need to get a CS by CA naught. To get that, we know that initially CA naught is CA plus CR plus CS, because whatever the concentration of A, it should be equal to the final concentration of A and final concentration of R and final concentration of S, because R and S is being formed only from A. Therefore, this equation it should be satisfied. So from that we can write CS is CA naught minus 1 by CA minus CS. So if you calculate that CS, CA naught is CA naught. CA already we calculated here, CA, and CR also we already calculated. So substitute it and then take CA naught common. So you can write CS by CA naught here, CS by CA naught, and take the LCM and cross multiply and do the LCM and do the simplification. If you simplify, there will be some terms which get cancelled out. So finally, you are left with this kind of equations. So CS is CA naught 1 minus e power minus K1t. If your K2 is much larger than K1. If your K2 is much larger than K1, K2 is larger, so K1 is small. So this term will be comparatively neglectable. So you can do that because K2 is much larger than. So you are left with this. And if K1 is much larger than K2, then you are left with this. Otherwise, if K1 and K2 both are very important, then you have to do with this particular equation, right? So we know that there will be a maximum concentration of R, that where it is going to happen. For calculating that, this particular thing should be integrated, and then if you put equate to 0, then you can get the concentration of CR, which is maximum. That is what we will do here. So CR is K1, this particular thing, CR is this. So integrate this, differentiate this and equate to 0, then you can get the maximum formation of R. So if you differentiate this expression, you get this, either this should be 0 or this should be 0. This cannot be 0 because CA naught is not 0, K1 is not 0. So only this term should be 0. Therefore, if that term should be 0, then you take the log and all, then you can get T mean or T, the time at which this CR maximum is happening, is nothing but ln K2 by K1 by K2 minus K1. That is otherwise called as K log mean. This is a log mean temperature. There are different means: log mean, arithmetic mean, geometric mean. This log mean, not only here, even in the heat exchangers you will get. Right? I asked you why you get a log mean, because here these are all unsteady state. That is, you get a curve. It's not a what do you call equation? What is that equation? Independent equations or dependent equations. This you cannot predict. You know the concentration here. You cannot predict what will be the concentration here with respect to the time, because this is highly non-linear. That is why you get if you want for an if you get a non-linear curves. So to calculate the mean, you have to go for a log mean. Not only here, even in heat exchanger, it is like that, right? So If it is a linear equation, then you can put a straight lines. Then having a known one point, you can predict what is happening, either interpolation or extrapolation you can do for a linear equation. For a non-linear equation, you cannot extrapolate or interpolate. That is why you get log mean, right? That very important term, why we get a log mean, right? So T, the time where the CR max is happening is nothing but, you know, K1 and K2. So substitute that K1 and K2 and try to find out its log mean. That mean is nothing but the temperature time at which this CR maximum is happening. So substitute this here in this equation, then you can get how much is CR max by CA naught. So it will come as K1 by K2 whole power K2 by K2 minus K1. So to 2 max questions also will come. How you calculate CR max by CA naught? They'll give you K1 and K2 values, right? So this is a very important 2 max question also. So for this, you need to give K1 by K2, right? So this already we derived, we didn't give much importance to it. This equation is true for CSTR, not CSTR, PFR and batch reactor. So in the first unit we did for a batch reactor. In the third unit we are doing for a plug flow reactor. The expression is same as the batch. So we need to do for a other one, that is CSTR, right? So before going to that, let us see the curves, how it is being happening. Now, if you draw C by CA naught, the concentration by CA naught versus K1 tau. So CA by CA naught curve will go down. And this is the CR by CA naught. We are much bothered about only CR, especially for a plug flow, CR by CA naught. So this will happen if your K1 by K2 is 0. So you are having one ratio K1 by K2 is in the form of K1 by K2 ratio. If K1 by K2 is ratio is 0, then you get this kind of curve. So this curve will change as your ratio changes. The CR by CR maximum will change when your K1 by K2 ratio is going to be changing. So as it changes, this is for K1 by K2 by K1 0. This is for 0.1. This is for 1. This is for 10. So as the ratio increases, you can see the concentration going down. So there will be everything high and then drop, high and then drop, high and then drop. So you can take the locus of this maximum rates, the locus of this maximum rate and draw a line. This will be the locus of the maximum R. So you need to maintain your reactant in such a reaction in such a way that you are at this locus. You are at this particular thing, your rate will be maximum and your maximum R will be formed. This is with respect to the unimolecular type reactions of how this R is being formed. There is one more, because R is formed, S is formed, and A is also formed. The relative rates of how much for how much A, how much R is formed and how much S is formed. This is the curve. You're drawing with the XA, that is 1 minus CA by CA naught, and y-axis is again the concentration C by C naught. So you can see here, it again depends on this K2 by K1 ratio, K2 by K1 ratio. So as the K2 by K1 ratio decreases, you see the curve is going like this, right? So as it decreases, this is for 10, this is for 1. So if you want, you put a straight line, the above it will be CA by CA naught. What is the conversion of CA by CA naught? And this in between is CS by CA naught. And this down is till whatever you are having, that is CR by CA naught, right? CR by CA naught. This gives you how much of R is formed, how much of S is formed, and how much of A is being reacted for XA. XA, it is closer to 1, that means more of A is consumed, right? So if it is closer to 0, that means more of yeah, CA also is formed. So CA is this much more of CA, because A is less, CA not is more, therefore you get less, right? So this is the different things for the plug flow. Now let us see for the mixed reactor and see whether the curve is going to be same in mixed reactor, that is Ca by Ca naught, Cr by Ca naught, or Cs by Ca naught, whether you get the same type of curves. That is what we will do for MFR now. So for a quantitative treatment of MFR, irreversible reactions in series, you need to do the material balance because continuous flow is there. Earlier also continuous flow is there, but we know that PFR and batch reactor is having the same plug flow same equation. That is why we did with a batch process. But here in MFR, you have to take a continuous process. Again, input is output plus disappearance, and if there are any unsteady state term is there, that is also will come into picture. Which for the reactant A becomes Fa naught is input is Fa naught flow rate, output flow rate is Fa. Disappearance is nothing but minus Ra into V. Disappearance is nothing but minus dCA by dt. So minus dCA by dt is nothing but minus Ra into V, because Ra is minus 1 by V into dCA by dt. So we want only dCA by dt, therefore minus Ra into V. So we can write in terms of the concentrations also. We know that Fa naught is nothing but the volumetric flow rate into Ca naught. Fa is again volumetric flow rate into Ca, volumetric flow rate. K1 Ra is, let us assume that is a first order reaction, K1 into Ca into V. So here you see V, V, V. This V is volume. This small v is nothing but the volumetric flow rate. So if you divide this V by V, V naught is nothing but tau m, that is nothing but the space time, or T bar, that is the mean residence time inside the reactor. So if you put that, then what will happen? So you can do that and then take this and take Ca terms to one side. Ca you write as Ca naught into 1 minus Xa and take Ca naught common. Then you can write Ca by Ca naught is 1 by K1 tau m. K1 tau m you get because V by V naught is tau m, right? So this is for Ca by Ca naught. Like that you can do for a component R also, the material balance. Material balance is VCR naught, because here we are writing for A. Next we should write for R, and like that you should write for S also. VCR naught is VCR plus minus R into V. Here we are putting, this is the appearance, disappearance, and this is also disappearance into V. So at any time, initially there is no R naught because only A is present, because this reaction is like this. No R is present, only A is present. Therefore, this is 0, this VCR, and RR is the nothing but the rate of disappearance of A. Rate of disappearance of A is this minus K1Ca plus K2Cr into V. Right? So this is 0. So you have to equate these 2 and 3 terms and put in this to give you the final form of the equation. Cr by Ca naught is K1 tau m by 1 plus K1 tau m plus 1 plus K2 tau m, right? So that is what K1, K2 you are having. So you get it. Again, here a lot of steps are being missed. If you want a detailed derivation, you can go in the Gawane. This is the Gawane book. I'll just increase it a bit more. Yeah, this is the Gawane book. So you can see here. So how he is being doing the derivation. Yeah, as I tell here in this presentation, he won't show you any what do you call derivations, but in Gawane he will give neatly, right? So this is how you get a Ca by Ca naught is 1 by 1 plus K1 tau m, because tau m Ca naught is Ca plus K1 Ca tau m. So take Ca outside, then write. So for R, yeah, this is how you are doing here. In this presentation, he just gave Cr by Ca naught from this step. So how it is being come, I just show you. Now you see, input of R is generation plus output. So this is the input, this is the generation, and this is the output. We CR naught is 0. So this is the generation and this is the output. So K1 CA minus K2 CRV is VCR. So you multiply with the V, and then tau m is V by V V naught. So CR you get as K1 CA tau m minus K2 CR tau m. So tau m cancel, what do you call thing. So CR into 1 plus K2 tau m is K1 CA tau m, because CR terms to one side and CA terms to one side. We know that CA is CA naught by 1 plus K1 tau m. So if you substitute this in this equation and then do it, then you are getting CR by CA naught is K1 tau m by 1 plus K1 tau m plus 1 plus K2 tau m. This is what is the thing which I am showing you here. So this remaining steps are not there. Please go and see in the governing. So this CR by CA naught is K1 tau m by 1 plus K1 tau m 1 into 1 plus K2 tau m. Like that, we need to calculate CS by CA naught, but we won't calculate it. We won't write the material balance, because we know that CA plus CR plus CS is should be constant. Either it is initially or the finally. So CA naught divide, if you divide the entire thing, CA by CA naught, CR by CS naught, CS by CA naught is should be 1. So CS by CA naught is nothing but 1 minus CA by CA naught and CR by CA naught. We already calculated CA by CA naught and CR by CA naught. Substitute it and then do. This is how you get CS by CA naught is this. Again, if you want the derivation, you have to see from the book. This is the book. That is what I'm just giving. CS is, where is this? Yeah, CS is CA naught minus CA by CR. So CS is CA naught minus CA by, CA is nothing but CA by this, CR is nothing but this. So you take the LCM and then you do it, then you will get CS by CA naught is K1 K2 tau m square divided by 1 plus K1 tau m 1 plus K2 tau m, right? So for this equation, CR by CA naught you are getting here. So we need to find out what is the R maximum. Again, you have to differentiate this and equate to 0. Then we can get where is the maximum. That is what is being doing. CR by CA naught is this. So differentiate that, equate to 0. This is a big term which will come because this square into this constant, this integration, differentiation, the minus this constant, this integration. Sorry, differentiation. That is what patiently you do, right? And some terms will get cancelled out. Finally, tau m you get as 1 by root K1 K2. Tau m is 1 by root K1 K2 is nothing but a geometric progression, am I right? Nothing but root K1 K2, that is B square is KC, right? So that it will be 1 by here. So this is the space time at which the maximum R is happened. Tau m is 1 by root K1 K2. This is for MFR. So where this concentration is maximum, again, if you substitute this tau m in this particular equation, 36.38, this particular thing, then you can get CR by CS maximum is 1 by K2 by K1 whole power half minus 1 whole square. This is the thing for MFR, right? So the derivations, again, I'm not giving the derivations. Please do by looking at that particular book, right? Because if I start telling all the derivations, then time would be enough. So here you are getting CR by CA naught is this for MFR, and tau m is 1 by root K1 by K2. This is for CSTR. Whereas you are getting, where is that? CR by CA naught is K1 by K2, K2 by K2 minus K1. This is for plug flow and mix, what do you call, plug flow and batch. T is 1 by log mean. This is for plug flow, whereas this is for MFR, right? So we can draw the curves now. CR by CA naught, CS by CA naught, 1 minus. This is the expression. CA by CA naught is coming down, but this coming down is not much greater. Whereas if you see here, CA by CA naught, it will go to almost 0. This is because there is no mixing in the plug flow equation, but since it is mixing, your CS by CA naught will not go to 0 here, and CR by CA naught is here, and you can see just like the previous one, but here you get more of CR by CA naught, but you are getting less of CR by CA naught here. So again, this is the locus of CR maximum. And if you want to calculate how much of CA by CA naught, CS by CA naught and CR by CA naught, that is comparative study of what is being formed. You can see here, more is being formed here. More of A is being reacted. You can see the curves as K1 by K2 ratio. But here, if you see, it again depends on this ratio K2 by K1. So less of that is being formed, right? So this is the comparative curves of the production of the different products with respect to this is MFR and this is with respect to PFR, right? So again, it again depends on this ratio K2 by K1. This is a very important thing. So this is comparing with the comparison of fractional yield of R in mixed and plug flow reactor for unimolecular type. Here it is giving XA in terms of XA. XA is 1 and XA is 0. Here is giving you in terms of fractional yields. This is R for a mixed and a plug flow reactor. So you can see it depends on K2 by K1. If it is K2 by K1 is 1, so the dashed line will give you the plug flow mixed reactor, and horizontal this what do you call thick line will give you for a plug flow. From this itself we know as it is 1, so you know you are getting more conversion in PFR than the mixed reactor for the same particular thing, for the same 0.6, for the same 0.6 or whatever the optimum thing. So this 0.6, this is the 0.6 curve. You can see less conversion, but 0.6 curve you get a 60% conversion in a PFR. You take any with any ratio, you can see here K2 by K1, K2 by K1 1. So as the ratio is decreasing, you are going towards this particular side. As the ratio is increasing, again still, always the plug flow is much better than the mixed reactor, right? So either it is series reactions or unimolecular reaction. This is the condition, right? So let us see some more types. Again, it depends on this fellow order. This depends on here you are assuming it is first order because your derivation entire thing you did with first order K1CA. But again, it depends on the order. So you can have A gives R gives S. K1 is first order, whereas K2 is zeroth order. So first order followed by a zeroth order. Then what will happen? Again, you have to do the derivation. Again, the same thing, CA by CA naught, CR by CA naught, CR maximum, CR maximum. So it depends on this order also. So again, you have to do the derivations. I didn't do the derivations. You have to do that. So you can see here, this capital K is K2 by CA naught by K1. That is what he's giving. Again, it depends on this K. So if you do that, you see here CA naught is coming down. CR is going to a maximum and then coming down. This is happening at TCR. That is what this 1 by K1 ln K1 by K2. CR maximum. And yes, if you see initially it goes up and then constant. It stays almost, it goes to the yes, right? So like this curves, you will get if you substitute the values, right? So how these curves are coming, all that you have to do the experiment and then do the draw the graphs, right? So like that, zero order followed by the first order. First order is 0, K1, and K2 is first order. Again, it depends. See, lot of values. Again, this is first order, this is second order, this is second order, this is first order. Different you will get, right? So here you can see for the this is zero order and this is first order. It goes to a maximum and then decreases. So this is your TR max, and the S curve, it goes on increasing till this and then starts increasing, right? So different trends you get. This is the initial slope and this is the initial slope 0, all that, right? So like that, you can do for a series parallel combinations. This will be very interesting. It's till now we saw only series or a parallel separately, but there are some reactions where this reaction, you see, A plus B gives R plus B gives S. So you see here, this reaction is parallel with respect to B, but this reaction is series with respect to A and B. A plus B is giving R. R is again reacting with B to give you S. So this is not only parallel, it is even series with R and parallel with B. Then how to do this kind of qualitative analysis? Again, very difficult to do the derivations. I don't think it will be much easier. This is only for irreversible. If it is reversible, then this becomes still complex. Like this, you can see this is Denby reaction, series and parallel. So you get a big terminologies. This we'll discuss in the next class, right? So I don't think time will be sufficient. I'll discuss this in the next class and do some problems and then wind off this third unit. Okay. Yeah, we'll do this series parallel combinations in the next class. I don't think time will be sufficient because it is already 9:25. So I stop here. Yeah, any doubt? Anyhow, you are not listening. Some of you will be listening, some of you are not listening. Okay, Guru, you're there, or Yamini, you're there. I think 46 people are there. Please give the attendance, take the attendance and send to me. I'll upload in the LMS. I observed a lot of you didn't submitted the second, what do you call this? Second, what is it? Tutorial assignment. A lot of people didn't submit it. And even the exam, I think more than some 12 to 13 people are absent. Please, the absentee people who are absent, please try to write the entire question paper, the solutions, and send me by mail, right? So assignment again, Guru, please take a note. The 12 absentees who are absent for the exam, you have to write that all the 12 people should write the question paper, entire question paper, and send to me by Monday, right? So I'm not giving much time. This is today, Friday. So before Monday, I think Sunday you can send to me because since exams are there, I'm giving that leverage to you. So Sunday you submit to me or maximum by Monday morning, right? Please submit to me. I'll give some marks. Otherwise, you have to give 0. That's all. Again, how many marks I give, it depends on me because I have to see if you are coming for 2 exams because only 2 exams will be counted, right? So submit that as an assignment. So all the answers with the question not required. The question paper you can take from the LMS, already uploaded in the LMS. Yeah. With that, I stop my recording and stop the sharing also.